Every digital device you own, from your phone to your car, from your gaming console to the data centers powering artificial intelligence, contains what we call a CPU, or central processing unit. Think of it as the brain, the conductor of an impossibly complex orchestra where billions of tiny switches called transistors turn on and off in precise coordination. Modern processors contain not millions but billions of these transistors, each smaller than a virus, all working together to make your digital life possible. But here's where the story gets fascinating. Take the M1 chip inside a modern MacBook, a marvel of engineering with over 16 billion transistors, capable of performing trillions of operations per second. Now compare it to the humble 6502 processor from the 1983 Apple IIe, a chip with just 3510 transistors that could barely run a simple word processor. On the surface, they seem like creatures from different planets entirely. The M1 is roughly 4.5 million times more powerful. Yet, astonishingly, they're distant cousins in the same family tree. This isn't just about Apple products. Whether we're talking about the GPU rendering graphics in your PlayStation, the processor in your Android phone, the chip controlling your smart refrigerator, or the massive AI accelerators in Google's data centers, they all share a common ancestor. They all speak the same fundamental language. They all operate on the same core principle that was figured out decades ago. So what is this technological DNA? It's not the transistors themselves. Those are just the building blocks, like cells in a body. It's not even the logic gates that transistors form. The real DNA is something more abstract, more beautiful. It's an architectural principle, a way of organizing computation that has proven so effective, so universal, that we've built our entire digital civilization on top of it. To understand this principle, we need to take a journey from the outside in. Imagine we could crack open your laptop like an egg, peeling away each layer to see what's inside. First, we'd remove the aluminum shell, revealing the battery that powers everything, the storage drive holding your files, and the DRAM memory chips that provide your computer's workspace. And there, nestled among the components, we'd find the CPU package itself. But even that package is just the beginning. Inside lies a heat spreader, a metal cap, that helps dissipate the enormous amount of heat these chips generate. Beneath that, we'd find an interposer, a sophisticated connector linking everything together. And finally, we'd reach the silicon die itself, a tiny square of crystallized sand, transformed through human ingenuity into the most complex object ever manufactured. If we could somehow zoom into that silicon die with impossible magnifying power, we'd see a city of transistors. Not a random scatter, but an organized metropolis with distinct neighborhoods. We'd see processor cores, the main engines of computation. We'd see caches, small, ultra-fast memory areas. We'd see specialized units designed for specific tasks. Each section has a purpose, each component has a job. Let's zoom in on just one performance core and reorganize what we see into a simplified diagram. At the most fundamental level, we'd witness something almost magical: transistors. Each just nanometers across, so small that thousands would fit across the width of a human hair, assembling themselves into logic gates. An AND gate here, an OR gate there, gates that can make decisions, gates that can remember, gates that can calculate. But these gates and transistors are almost impossibly abstract. How do we make sense of something happening at a scale our minds weren't built to comprehend? This is where a beautiful analogy comes in, one that will help us understand how your computer really thinks. Imagine a room. In this room, there are several key elements: tall bookshelves lining the walls, a wheeled cart, a table, a calculator, and a tireless robot that follows instructions perfectly. This simple setup is actually a perfect model for understanding your CPU. The bookshelves represent your SSD or hard drive, long-term storage, where all your programs and files live as books waiting to be accessed. The cart represents your DRAM, the temporary workspace that holds whatever you're currently working on. The table represents the cache, an even faster, more convenient surface for immediate access. Scattered across the table are pieces of paper. These are your registers, the absolute fastest form of storage, holding the numbers and values the CPU is working with right this second. And that calculator? That's the ALU, the arithmetic logic unit, the actual muscle of the CPU. It can add, subtract, multiply, and divide. It can perform logical operations, comparing whether one number is bigger than another. It can shift bits around, manipulate data in precise ways. The ALU is where computation actually happens. The robot controller in our analogy represents the control unit, the part of the CPU that orchestrates everything, reading instructions and making sure each component does its job at exactly the right time. Now, what exactly is a program? In our analogy, it's a book pulled from the bookshelf. But this book contains two types of pages: instruction pages and data pages. The instruction pages tell the robot what to do. Pick up this number, add that number, store the result here. The data pages contain the actual numbers and information being worked with. When you double-click an application on your computer, you're essentially telling the robot to pull a specific book from the shelf, wheel it over on the cart, and start following its instructions page by page. Simple instructions might look like this. Load this value from memory into a register. Increment it by 1. Store the result back to memory. Every program you've ever run, from simple calculator apps to complex video games to artificial intelligence models, is ultimately just a very long sequence of these simple instructions. It's like building a cathedral one brick at a time. Each brick is trivial, but together, they create something magnificent. But how does the CPU know which instruction to execute next? This is where the program counter comes in, a special register that keeps track of the current position in the program, like a bookmark. After each instruction executes, the program counter automatically moves to the next instruction. Except sometimes we don't want to go to the next instruction in sequence. Sometimes we want to jump to a different part of the program, or repeat a section multiple times. This is how loops work, how decisions work, how programs gain their flexibility. A jump instruction tells the program counter to leap to a different location. A conditional branch says, if this condition is true, jump to that instruction. Otherwise, continue normally. Think about a simple for loop that counts from 1 to 10. The program loads the number 1, compares it to 10, performs some action, increments the counter, then jumps back to the comparison. This cycle repeats until the counter reaches 10, at which point the program moves on. 10 separate operations, achieved through a handful of simple instructions executed in a loop. Now we arrive at the most important concept in all of computing. The technological DNA I mentioned earlier. The Fetch-Decode-Execute cycle. This three-step process is the heartbeat of every CPU ever made, from the earliest mainframes to the chip in your pocket right now. First, fetch. The CPU retrieves the next instruction from memory, using the program counter to know where to look. Second, decode. The CPU interprets that instruction, which is just a pattern of 1 south and 0 south, and translates it into control signals. Complex logic circuits transform binary codes into precise electrical commands that will orchestrate the movement of data throughout the processor. Third, execute. The CPU carries out the instruction, whether that's performing a calculation, moving data, or changing the program counter. Then the cycle repeats. Fetch, decode, execute. Fetch, decode, execute. Billions of times per second. This cycle runs, never stopping, never tiring, processing your emails, rendering your videos, running your games, training AI models, managing power systems, controlling aircraft. All of it rests on this elegant three-step dance. What keeps this cycle synchronized? A clock signal, a precisely timed electrical pulse that acts as the heartbeat of the CPU. Early computers ran at clock speeds measured in kilohertz or low megahertz, executing thousands or millions of cycles per second. Modern processors operate in the gigahertz range, billions of cycles per second. The M1 chip, for instance, can execute over 3 billion fetch-decode-execute cycles every single second. But modern CPUs don't just run faster, they've gotten smarter. Through techniques like pipelining, they can work on multiple instructions simultaneously, like an assembly line where different parts of different cars are being built at the same time. While one instruction is being executed, the next is being decoded, and the one after that is being fetched. This parallelism is how modern processors achieve their incredible performance. Not every computing task needs the flexibility of a CPU. ASIC's application-specific integrated circuits trade versatility for extreme efficiency at one specific task. The chip in your USB charger doesn't need to run arbitrary programs. It just needs to regulate voltage. So it uses an ASIC. FPGA's field programmable gate arrays offer a middle ground, allowing hardware to be reconfigured for different tasks. And quantum computers represent an entirely different paradigm, using quantum mechanical properties to solve certain problems in fundamentally new ways. But for general-purpose computing, the CPU architecture with its fetch-decode-execute cycle remains supreme. It's why your phone can run thousands of different apps, why your computer can browse the web and edit videos and play games. That flexibility is the whole point. Of course, I've simplified things. Real CPUs include additional steps like memory access and write-back, dealing with the fact that retrieving data from RAM can take hundreds of cycles and eternity at CPU speeds. Modern processors include multiple levels of cache memory precisely to avoid these delays, keeping frequently used data close at hand. And above the hardware level lie countless layers of abstraction. Machine code becomes assembly language, becomes high-level programming languages, becomes applications, becomes the user interface you interact with. Each layer builds upon the last, hiding complexity, making the impossible possible. The debate between RISC, reduced instruction set computing, and CISC, complex instruction set computing architectures represents different philosophies. ARM processors, like the M1, use RISC simpler instructions that execute more efficiently. Intel x86 processors use CISC, more complex instructions that can do more in a single step but require more power. Each has trade-offs, but both still use the same fundamental fetch-decode-execute cycle. When you peek inside a real M1 core, the simple analogy we started with expands dramatically. Multiple ALIs working in parallel. Branch prediction units guessing which instructions will be needed next. Specialized execution units for floating-point math, for vector operations, for encryption. Pipelines 12 or more stages deep. Sophisticated caching hierarchies. Out-of-order execution that rearranges instructions for maximum efficiency. And modern chips aren't just CPUs anymore, they're SoCs, systems on a chip, integrating CPU cores alongside GPU cores, AI accelerators, image processors, security modules, and more. The M1 includes an 8-core GPU capable of processing graphics through massive parallelism, thousands of simpler cores working on different pixels. Simultaneously, all coordinated in what's called SIMT, single instruction, multiple threads execution. Yet beneath all this sophistication at the absolute core, the fetch-decode-execute cycle still beats on, unchanged in its fundamental essence from the processors of 50 years ago. Here is what strikes me most about this story. Sometimes the most powerful ideas are the simplest ones. Refined and perfected rather than discarded. In a world obsessed with the next big thing, the CPU reminds us that elegance and fundamentals matter more than constant revolution. In your own life, what are your core principles, your personal fetch-decode-execute cycle? What simple routines or values, if executed consistently and well, could compound into extraordinary results? Just as a CPU executes billions of simple operations to achieve complex tasks, what small actions could you repeat daily to build your own masterpiece? The engineers who designed the M1 didn't abandon the wisdom of the past, they honored it, building upon a solid foundation while adding modern innovations. How might you do the same in your field, your craft, your life? So I'll leave you with this, knowing that your devices all share this ancient, elegant heartbeat, this same cycle repeated billions of times per second. Does it change how you think about technology? Does it make you appreciate the devices you use every day just a little bit more? Or does it inspire you to learn even deeper, to perhaps study computer science yourself? I'd love to hear your thoughts in the comments below. What fascinates you most about how computers think? What questions do you still have? Remember, whether you're coding the next great app or simply sending a text message to a loved one, you're participating in one of humanity's most beautiful intellectual achievements. 50-year-old idea that still powers our world. Stay curious, stay healthy, and keep learning. The world of technology has so many more secrets to reveal, and I'll be here to help you discover them. If you found this journey worthwhile, subscribe to the channel and join me next time as we explore another fascinating corner of the digital universe.